So now that we're moving into ANOVA, we need to think about it a bit more critically because we're moving into the two-way ANOVA model, the two-way omnibus. We've spoken a little bit about the technicality, but I just want to bring it back to your attention. This ANOVA model is going to highlight if there are differences within each IV. So this is a main effect, and this is averaged across the levels of the other IV. So when we were talking about the main effects before, when we were talking about differences between gender averaged across the amount of alcohol, that's what this will be. The differences of each IV are main effects averaged across the levels of the other. The ANOVA will also highlight the differences between groups of one IV dependent on the levels of the other. So this is the interaction. This is that difference of differences we were looking at before. Is the difference between 0 and 2 pints for male the same or different to that of 0 and 2 pints for female? If any of these differences are significant in their size, the ANOVA will not tell us where it is, simply that there is one somewhere. It will tell us if it lies within one of the main effects of the interaction, but not exactly where the comparison is. The null hypothesis hasn't changed. The one technicality now is we have a null hypothesis for each main effect, so there's two null hypotheses there, and a third one for the interaction. So for gender, the null hypothesis is that the mean of males will equal the mean of females. For pints, it's going to be that 0 pints equals 2 equals 4, and then for interaction, it's going to be males at 0 equals females at 0 equals males at 2 equals females at 2 equals males at 4 equals females at 4. So we'll have 3 null hypotheses. This means we're going to have 3 significance tests. Now, when we started ANOVA, it was to minimize the amount of significant tests that we were running. So how can we now justify having 3 significance tests? Haven't we inflated type 1 error? And the answer is, well, actually, no, we haven't. Each of these main effects and their interaction are what we call, the technical term is actually orthogonal, in that the variation in these variables actually don't overlap. They are separate analyses. So a way to think about it, in previous weeks we've always used this circle, and we've said this circle represents all the reasons why someone got the score they did. In a two-way ANOVA, we actually have 3 separate circles. So the issue with type 1 error rates going up with multiple comparisons is that, let's say this is the overlap between our DV and the IV, and then let's cut this up a little bit, and let's say that these are the reasons why level 1 explains the DV score, this would be level 2 of our IV, and this would be level 3. So the issue with multiple comparisons is when you compare this chunk to this chunk once, but then this same chunk here gets compared a second time. And so you actually take this same chunk of variance and you compare it over and over again. That's an issue with type 1 error, because if there's an error in this blue chunk here, then that error gets taken over to all the other tests that it's used in. But in a two-way ANOVA, we actually have a main effect here, a main effect here, and a main effect here. And so when we actually look at their relationships with our DVs, with our DV, each one is a separate chunk of variance. So because each is a completely separate thing, they are totally orthogonal to each other, it's perfectly fine to have 3 p-values. It would be the same as if I ran 3 tests over 3 studies. But when we get into looking at the comparisons within each IV, then we're going to have to start adjusting. Okay, so the syntax here is pretty straightforward. It's ANOVA, attract, so that's our DV. Then it's our 2 IVs, sex and pints. And then to get their interaction, we need to go sex hashtag pints. Now, there's a shortcut. If I go sex hashtag pints, it will actually put in the main effects for me. So this syntax here is the same as this syntax here. It does the same thing. The only difference is I have 2 hashtags here, and that forces the IVs to go in as well. If I only had 1 hashtag, like this, then it would only put the interaction into the model. And we can't have that. So in ANOVA, you have to have the main effects in the model for the interaction to make sense. If you don't have the main effects in the model, the interaction is a really weird, wishy-washy thing that doesn't have any real interpretation. So this is the syntax. If you do the full syntax, then you'll be sure that you'll always have the main effects. If you want to take the shorthand, make sure you have a big, massive note in your notes saying to use 2 hashtags. So let's run the ANOVA command first, then we'll look at the margins and margins plot command. So this is our ANOVA table. We can see there are 48 people in our study. Our R-squared is 0.61, which tells me that 61% of the variance in attractiveness is related to the gender, the amount of alcohol they've consumed, and the interaction of the two. Now, the last 2 weeks, our model line has been the exact same as our sex and as our main effects line. But now if we look, it's totally different. None of those numbers even look remotely the same except for this p-value here. And I can guarantee if I had that to infinite decimal places, they would not be the same either. What's going on is we have each of our effects laid out one by one. So we have our gender variable, our alcohol variable, and we have their interaction. This model line is the combined effect of all 3 IVs. So if all 3 IVs had a non-significant effect, the overall model, this p-value, would also be non-significant. If at least one of these are significant, so one of our main effects or interactions are significant, then the main effect will, the model, will also be significant. So the model then is just all of these combined together. The degrees of freedom are added up, so 1 plus 2 plus 2 is 5. Then if we take partial sums of squares divided by the degrees of freedom, I get a mean sums of squares of 1095. If I was to divide 1095 by the residual, I would get 13.20. And if I compared that to an F table, which we're not doing today, but we will do in the future, I would see that that is larger than its critical F. And I know this because my p-value is significant. Now, we don't normally interpret the model line in this course, but that's there for you just so that you know what it is. Otherwise, you can just ignore it. In other courses, you will be interested in that line. Now, if we come down to our 3 variables here, sex, pints, and the interaction. I'm ignoring the residual and the total because we've already gone over those in previous weeks. Our sex line represents the main effect of gender, averaged across alcohol. Our pints line represents the main effect of the amount of alcohol you've consumed, averaged across gender. And then our sex pints interaction is looking at the individual cells within. So just to remind us, our sex variable then is comparing these 2 means together. Our pints effect is comparing these 3 means together. And then the interaction is comparing the cells. And I can actually tell this by looking at the degrees of freedom. Sex has 1 degree of freedom, which means it must have 2 groups. And I know that it must have 2 groups because if I go back and think about the formula, degrees of freedom for our IV, there we go. Degrees of freedom for our IV is k minus 1. So, if degrees of freedom for sex equals 1, then degrees of freedom for sex must equal k minus 1. Sorry. If degrees of freedom for sex equals 1, then what I know is that 1 must equal k minus 1. And then with a little bit of algebra, I can add 1 to both sides, which tells me that k equals 2. So using that little bit of algebra, I can actually reverse engineer the number of groups. So whenever you know the degrees of freedom, you can figure out the number of groups by adding 1. So sex has degrees of freedom of 1, I add 1, that tells me that k equals 2. Or in other words, that there are 2 groups for gender. For pints, 2 plus 1 would be 3. This doesn't work for the interaction. The degrees of freedom for the interaction are calculated a little bit differently, despite the fact that there are 6 means. And the reason for this is you still need to maintain the data structure that it's 2 by 3. So to calculate the degrees of freedom for the interaction, I actually multiply my degrees of freedom together. So it's 1 times 2 would give me 2. If my sex variable had a third group, say transgender or non-binary or some other third category, I could actually then have a degree of freedom of 2 for gender, and then my interactions degrees of freedom would be 4, because it would be 2 times 2 is 4. Other than that, the interactions effect is exactly the same as any other effect. I take my sum squares divided by the degrees of freedom, and I'll get 989. I take that and I divide it by 83, so 989 divided by 83 gives me about 11 and a bit. And I can look up an F in an F table, compare it, go, oh look, it's larger. Or I can look at my p-value here and go, okay, it's less than 0.05. My interaction is significant.